Okay, so hello and welcome to the video session for today. So this time we are going to have examples on tributary areas, how these tributary areas shall be transmitted on the structural member. And we should know first the tributary area, whether it is a one-way system or two-way system. So in this case, we have here a floor of a classroom is to be supported by the bar joist shown in this figure as well as this figure, and it is 15 feet long and spaced 2.5 feet apart. The floor itself is to be made from the lightweight concrete that is 4 inches thick. Neglecting the weight of the joist, we are going to determine the load that acts along is joist. So meaning it is just the distribution that we need to compute. So if we are going to have the top view of that, so maybe we have the top view, say here, we have a series of joists that are equally spaced, and this is spaced within 2.5 each, 2.5 feet each. Okay. So this is 2.5 feet apart, and we have here 15 feet. So recalling our initial knowledge on one-way and two-way slab, we should investigate the ratio of the longer dimension to that of the shorter one. So L over S should be greater than 2. This is one-way system. And if the longer dimension to the shorter one is less than or equal to 2, this should be treated as two-way system. So as a clue here, a one-way slab look like this. There is an obvious rectangular section wherein the longer one is twice the shorter one, okay, or more than twice the shorter one. So that is the rationale. And if we have a two-way system, we have only a slight difference between the longer dimension to the shorter dimension. So looking at the figure, what do you think? It is falling under two-way slab. One-way system. Why one-way system? Because it is obvious that even if you are going to do double 2.5, it is only 5, it will not reach 15. So meaning 15 is much greater than the double of the shorter one. So obviously, that is one-way system. So L is the longer span all over S, that is 2.5, and that is equivalent to 6. And 6 is far greater than 2, therefore it will fall on one-way system. So if it is one-way system, we do not have to create a 45 degrees line on the edges and then have this as its distribution, okay? But we are just to consider the half of the dimension of the adjacent flooring, both ends, okay? So if that is the case, we will be having a tributary area 15 by 2.5. Just the same, this is 2.5 because although we have them, they have both half of 2.5 at both ends. Okay, so except for the last beam here, because for the last beam it will just carry a single coverage of the half of the 2.5. So this is 2.5 all over 2 on the edges, but we are trying to compute here the maximum loading of this joist in the system. So with that, we are now going to determine what will be the loading of this floor system. So in the problem, we should know what is the material that is being carried by this floor joist. At the same time, what is the occupancy? So in here, we have a classroom as the occupancy, and the material is a lightweight concrete that is 4 inches thick. So first, let us look into the table containing the dead load. So I think we should refer to table 1-3. We have here a floor fill that is a lightweight concrete according to the problem, and that is 8 pounds per square feet for the English system per inches. Okay, floor fill lightweight concrete plane per inches. So the unit here is pounds per square feet per inches. So that is equivalent to 8. So do not neglect the unit because that will be your basis. So we have 8 pounds per square feet, and this is per inches at the same time. How many inches? According to the problem, we have here a 4 inches. So if we're going to calculate that, this will just be cancelled. And obviously that is 32 pounds per square feet. Okay? So express first all the gravity loads in terms of pounds per square feet. Now moving on to the live load, if we have a classroom, we have a classroom that is equivalent to 40 PSF as the live load. So the live load here is 40 pounds per square foot. Okay? So if we are going to add that one, all in all, we have a total load in terms of pressure. Obviously, 32 plus 40, that is 40 pounds per square foot. And then next, we wanted to distribute this pressure along the length or along the long direction. So why along the long direction? Because there will be no support along the short direction. At the same time, if we have a one-way system, the shorter dimension has no load to carry. Okay, so remember that. So basically, we are going to multiply this 40 to the area. And what will happen if we are going to multiply it by the area? Feet squared here will just be eliminated, and 40 pounds will just be the resultant. Okay, so the 40 there it is. It will become a resultant if it is being multiplied by 2.5 by 15. So we'll be having here a resultant, and this resultant will be distributed along the length. Okay, so that is the rationale. If this R will be distributed along the length, it will become a uniform distributed load along the length. So that is the pattern of the solution. So let us do that. We have to multiply it by 2.5 by 15. So this is actually the tributary area. So this now becomes feet squared. That is just cancelled. So we will be having 1,500 pounds. So we are going to distribute along the length. So therefore, the W here, or the distributed load along the long direction, is equal to 1,500 pounds. Where shall you distribute? Along the 15. So therefore, this is divided by 15 feet. And then we have here 1,5. Sorry. I'm so sorry. But we have 32 plus 40. That should be 72. Okay. So sorry for that. 72 by 2.5 by 15. May we recalculate that one? This shall be equal to 2,700. Okay. 2,700 pounds. And the next, just the same, we divide it by the length where we wanted to distribute this 2,700 divided by 15. We have 180 pounds per feet, and this is the answer for this problem. Okay, moving on to the second problem. We have here a flat roof of the steel frame building shown in the photo is intended to support a total load of 2 kN per square meter over its surface. Determine the roof load within region ABCD that is transmitted to beam BC. The dimensions are shown here. So obviously, on the dimension, it has already indicated that this is a two-way slab because it has drawn already a 45-degree line on each of the edges, and then we have here a trapezoidal loading for the longer span and a triangular load for the shorter span. However, if this is not indicated in the problem, what is important that we all know the dimension of this figure. So granting that this is equal to 5 meters on the figure and this is 4 meters, we can check the L over S, or the longer dimension to the shorter dimension. This is 5 all over 4. So obviously 5 over 4 is 1.25. Now this 1.25 is less than 2. Okay, so in short, there is only a slight difference between L over S. And if this is the case, then we can say that this is a two-way system. Okay, class? So if it is a two-way system, again, we are going to have a lines here drawn 45 degrees on each of the corners, and then just intersect it with this line. Okay, so again, do not bother yourself by computing the area and then multiply it by the loading and then divide it by the length where you wanted to distribute. So what you do is just multiply the area, or we just multiply the loading in pressure. Okay, loading in pressure is per square foot or per square meter. Okay, so what you do you search for the triangle. Do not go for the trapezoid. So where's the triangle? Here's the triangle. And then look at the dimension of the triangle, or the length of the triangle, that is 4 meters, of course. And then next, you divide 4 meters into 2. Okay? Why? Because as we can see here in the trapezoid, it bisected the 4 meters here, and obviously this is 2 meters. So we are actually determining the peak of the W, and the peak of the W is on the range, on this range. So next, we're going to have an illustration for that. Okay. We have here a distributed load. However, this is not uniformly distributed. It is a trapezoidal one. Of course, we are going to have the W along the L, and then along the short dimension, we also have a triangular one, and the highest loading here is W, okay, and then it will yield to 0 at both ends. This is the shorter one. So what you do is to get the loading first, and then we will look into the distribution by and by. In the problem, the total load is already given, so we do not need to refer to any table here. So 2 kilonewton meter per squared covers all the gravity loads that we need. So the total loading is 2. So therefore, distributed W along the long direction is equivalent to the pressure, that is 2 kilonewton per square meter. So we're just gonna multiply this by the half of the dimension where the triangle is, that is 2. So as a summary, we have actually introduced that W in here is the pressure times the half of the shorter dimension. Okay, so what is the shorter dimension? That is 2 meters. So eventually we cancel one of the meters here, and automatically this is 4 kilonewton per square meter. 4 kilonewton per meter. Okay. So moving on to the third problem. We have here the third problem. So for the third problem, we have here a concrete girder. So as we can see in the photo, we have an interior girder here. So when we say interior girder, there will be two slabs that is being carried by the girder. So if we're going to illustrate that one, we have this girder, and this girder is about 15 feet apart. So this girder is 15 feet apart. Okay, see, this is 15, and the length is 30. So this is the orientation of the girder. Wherein first we need to know what is the orientation of the girder. Is it a one-way system or two-way system? Of course, we're going to investigate L over S, or the longer dimension to the shorter dimension. We have 30 all over 15, that is equal to 2, and 2 is just equal to 2, right? So what is the indication? If we have L over S to be less than or equal to 2, that is treated as two-way system. So again, when we have a two-way system, we need to draw a 45 degrees line here, so that the longer dimension will carry a trapezoidal load using the peak W, as well as a triangular load for the shorter span using also the peak W. So again, do not bother yourself calculating the trapezoidal area and the rectangular area here. So it is good to note also the distribution of the trapezoidal load according to the length, and we should note the transition between the highest peak up to where it will come back to 0. So let us draw now the beam. So if this is the longer beam, there will be a trapezoidal load here. Okay, so let us note now the dimension. So what will be the dimension of this one? Okay, so basing from this triangle, of course this is a 45 degrees, and we all know that a 45 degrees right triangle has equal legs, right? So it will have an equal leg for this right triangle, so that if this is S, then that should be also equal to S. Now, if we're going to have this to be 45 degrees, the line here is a bisecting line along the short direction, isn't it? It is obvious this is a bisecting line, meaning 15 will just be bisected into 2. This will be 7.5, so that this bisecting line is also 7.5, because this is 45 degrees. Applying the principle, if we have a 45 degrees, they have an equal leg to that. So in short, therefore, this is 7.5, and this is also 7.5. So therefore, this is 15 in dimension along the longer span. For the shorter span, we'll just have to consider the shorter span, but the same W, or the peak W, that we need to derive here, the peak W. So what is the dimension of the shorter one? The whole dimension, which is 15 feet. Okay, 15 feet. So now we'll just have to compute for the W. So in order to come up with the W, do not bother yourself by computing the areas. Just compute for the area of the trapezoid and compute for the area of the triangle, and then divide it by the length where you want it to distribute. So that is not the procedure for the two-way slab. All we need is the pressure caused by the gravity loads caused by the live load or the dead load, and then just multiply it by the half of the shorter dimension. So the step is simplified into that. So what we do is just, when we have a two-way slab, of course, first you draw here a 45 degrees line, and then search for the triangle. So where's the triangle? Here's the triangle. And then search for the dimension of this triangle, or the length of the base is 15 in this case. So all you have to do is draw a bisecting line there, and this is already 7.5, which will be the multiplier for your derived pressure, and that will be our W, or the uniform distributed load, or the peak distributed load on this trapezoid as well as this triangle. Okay, so again, search for the triangle. Between the trapezoid and the triangle, search for the triangle, get the dimension of the triangle or the base. In this case, that is 15. Just divide 15 into 2 because we have here the bisecting line, and then that is your multiplier now. So knowing now the multiplier, we'll just get the total load caused by the gravity load. So in this case, what are the gravity load carried by this girder? So we have here a floor slab that is 5 inches thick, and it is made of reinforced stone concrete. So we refer to the table referring to that material. Okay? So referring now to the table, we have here the table. We have two available tables, whether we use the pressure or we use the unit load, whichever is convenient to us. So on the table, table 1-2 presents a table of pounds per cubic feet. Okay, and for the other one, it is in terms of pounds per square feet. So remember, we're looking at a reinforced stone concrete. So in this floor fill, if we are going to have the floor fill, let us recall that table 1-3 came about table 1-2. Say for example, the floor fill, it is in terms of pounds per square foot, and this PSF is derived from PCF. How is that? So let us investigate this. A cinder concrete per inch. Do we have a cinder concrete here? Yes, we have. So that is equivalent to 111. Okay? So meaning, if we have pounds or 111 pounds per cubic feet, if we are going to multiply that by a feet, becomes PSF, right? Pounds per square feet. Now, this 111, we are going to express that into per inches. Okay? So if we are going to have a per inch unit there, say 111, 1 inch is actually, 1 foot is actually 12 inches. So therefore, we have here 9.25 PSF. Do we have 9.25 here? None. Perhaps we have a mistake in selecting what is cinder here. Okay, so cinder here perhaps is not a reinforced cinder. Okay, so looking back to the table 1-2, it is actually 108. Okay, so let us try that one. So 108 divided by 12, that is 9. So exactly 9 PSF. So meaning this plain cinder here, okay, cinder came from, that is not a reinforced. This plain cinder here came from this. Okay, so 9 came from 108. And then concrete plain stone, 144 over 12 is 12. Okay, this one. Okay, stone concrete per inch is 12 pounds per square foot per inches. And then the lightweight concrete, we do not have a value for the lightweight concrete here. So that's it. The value for table 1-2 came from, the value from table 1-3 came from 1-3. However, there are items that are not found in table 1-3, and some items are also not found in table 1-2. Comparing the two, there are items that it is present in table 1-2, but it is not present in table 1-3, and vice versa. In this case, in this problem, we are actually looking at a reinforced stone concrete. So looking at the table 1-3, when we investigate the floor fill, we have a cinder, lightweight stone concrete. Is it the stone concrete? I think not, because on the problem, it specifies that is a reinforced stone. It is not a plain stone. So, meaning, in table 1-3, we cannot find that item. So therefore, again, we go back to table 1-2, because table 1-2 contains that item, and that item is actually this one. Reinforced stone concrete, that is 150 pounds per cubic feet, and pounds per cubic feet will be treated differently from this one, because this one will just have to multiply it by the thickness and that's it. But this time we are going to multiply also by the thickness, and it will become the pressure. Okay, so 150. So we now go back to this. So W will be derived from the total gravity load. So first we have the dead load, and that is reinforced stone concrete. So we already referred to the table. That is 150 pounds per cubic feet. And then, what should we do? If we multiply it by the thickness, Of course, we must have to be consistent. Say that is 5 inches. However, this 5 should be converted also to feet to adhere with the feet unit. Okay, so there are 12 inches in 1 foot, so that we can cancel that one, and then 5 will be in terms, or the thickness will be in terms of feet. Now this is cancelled. So all in all, we have 150 times 5 divided by 12, that is equivalent to 62.5 pounds per square foot. Okay, and then for the live load, it is already in the given, so 50 pounds per square foot. So we will do nothing to the live load. That is already pegged to be 50 pounds per square foot. So adding the two, therefore we have 112 pounds per square foot. So next, what will be the tributary load of this long direction? Again, the tributary load is a two adjacent slab. Okay, two adjacent slab. Okay, so if we're going to divide the 15, 7.5, and this is also 7.5, just the same, this is also 15, and that is 30. So if it is a two-way slab, again, we are going to have a bisecting line on the edges that is 45 degrees. So finally, W is equal to, let us just carry that one, the pressure multiplied by the half of the dimension of this triangle. What is the dimension of this triangle? 15. Half that one, that is 7.5. 7.5. This is feet. And then finally, W is 112 times 7.5 sorry 112 pounds per square foot times 7.5 we have 62.5 plus 50, that is 112.5. Sorry, that is 112.5. So this should be also 112.5 pounds per square foot times the half of the 15 triangle there, 12.5 times 7.5, that is 843.75. So we have 843.75. So this W carries a single trapezoid here. Remember that. Okay. A single trapezoid carries 843.75. Now, if we refer to the interior beam, as we have said, it carries two dimensions, so that it will carry two 843.75. So W for the girder total is 843.75 multiplied by 2, that is 1687.5 pounds per feet. So why is that? Again, let me explain that one. If these are the girder, okay, we have the tributary areas. Of course, this is 15 and that is 15. All right. So what we have computed here is a single span of the trapezoid, that is 843.75. But what about the other one? That is why we are multiplying it by 2, or we just twice it, because these are identical trapezoid here. That is why we have 843.75 times 2. All in all, we have 1687.5 for this girder to carry. Okay, for that girder to carry. For this girder to carry. Okay? So for the shorter dimension, it will just carry a single triangle here, equivalent to 843.75 as the peak W for the shorter dimension. And for the longer dimension, we have 1687.5, which is a trapezoid one. So this is 15, 7.5, that is 7.5. This is 1687.5. Okay, so that's it for this problem.